Okay, now let's move on to thermodynamics. Okay. First, we're going to start off with heat transfer. So there are three methods of heat transfer. I think this is the most important part of like thermodynamics for the MCAT that you really have to know. Conduction, convection, and radiation. Conduction is direct heat transfer from physical contact. Example, you touch a hot frying pan. Touch a hot frying pan, heat goes from the frying pan directly into your skin, right, by direct contact. Next is convection. This transfers from a surface to a fluid, and it results in the subsequent movement of the fluid as a result of being heated. Note, this is via a fluid, not a liquid. So convection can occur through gases as well, not just liquids. Okay. For example, water being boiled in a pot. The heat goes directly from the very hot pot directly into the water, which is a fluid or a liquid. And the liquid, it ends up moving a lot in the pot. As a result, the water molecules end up moving a lot. So the hot ones go to the top, whereas the colder ones rise, and then they get heated up, and then it's just a cycle of movement. Okay. And then lastly is radiation, which is no direct transfer required. It transfers energy via transfers thermal energy via electromagnetic waves through space. For example, a campfire just emits heat. You don't need to touch the fire. You don't need to have like any kind of fluid necessarily, although the fireplace will also heat the air around because it is fluid, but like the actual fire itself is not physical, it's not a surface. So it transfers heat through electromagnetic waves. It's the fire is not an object, right? You can't really touch fire because it's not really an object, it's more like an energy, right? And this is just a graph showing this. Conduction is directly touching a stove. Convection is you heat the water from the pot, the bottom of the pot heats the water, and then the hot air rises, warm air falls, and then it just goes in a cycle. And lastly, radiation is just a campfire or something like that. It's transferring heat through electromagnetic radiation, right? Next up is state versus path functions. Chemistry, there are state and path functions, which are properties very similar to conservative and non-conservative forces, in that state functions are properties that do not change based on the path taken to get to the value. For example, change in pressure, volume, temperature, enthalpy, entropy. And these are properties that are innate to the process. For example, if you turn water into ice, right? The pressure, the volume, whatever, it doesn't matter how you turn the water into ice, it'll be the same. The enthalpy, the entropy, Gibbs free energy, all of those don't change regardless of how you actually turn the water into ice, right? It's just the start point and the end point. Whereas path functions do change based on the path you take by the process. For example, heat and work. So there are some ways to turn water into ice that maybe use up a lot of heat, whereas other ways use up less heat. Some that require more work, some require less work. It depends on which path you take. Path functions are not properties of necessarily the process itself, but rather the steps taken, right? So heat is not a property of turning water into ice. It's a property of the specific way you turn the water into ice, right? Okay. Path functions implies rely on the path. State functions are part of the state. They're not related to the path. Okay. Next, I know we're jumping through a lot of different topics. PV diagrams. So the PV diagram is kind of important, and I think it is important, especially as some important vocabulary that you should know. The PV diagram shows the relationship between pressure and volume for a certain system. So again, if we're talking about water to ice, it might, or like some kind of gas diagram, we might want to look at like this PV diagram for specific gases that are being used, and usually it's for gases, not liquids or solids. So yeah, as you can see here, there are 4 different types of reactions that you will probably see on a PV diagram: isobaric, isothermal, adiabatic, and isometric. What all these mean? Well, isobaric is constant pressure, and if you look, pressure's on the y-axis. No matter how much you change the volume, the pressure is always going to be at this, which is like, for example, like 10. No matter what volume it is, it's always just going to be at 10 because it's constant pressure. Same thing with isometric, which is constant volume. Let's say this is like 3, right? These are just made up numbers, but yeah. No matter what the pressure is, the pressure can go up. The volume will still always be 3. Next is, these are a little more complicated, isothermal, which is constant temperature. This is what things like Celsius, Kelvin, Fahrenheit measure, temperature, right? Isothermal is temperature. Looks kind of like this, right? And then adiabatic, which is constant heat, which is not the same thing as constant pressure or constant temperature. Temperature and heat are 2 different things, and I think I covered that a little bit in the previous thermodynamics lecture, but I really recommend you knowing the differences between temperature and heat because they are not the same thing. Temperature is usually written as things like Q, right? Whereas temperature is written as like T, for example, but they're not the same thing. So constant temperature, constant heat, adiabatic, also looks kind of similar to isothermal, but like this. And these obviously change depending on the process. It's just like kind of like this is the trend, I guess, right? So adiabatic might be like here or like something like that, right? Or like here. But this is generally the shape it will be. And remember, the work done is always equal to the area under the curve. Again, just like integrals kind of, but you do kind of have to know a little bit of basic integrals for the MCAT, but like this, like for isobaric, this would be like the shaded region. So find the area under the curve, right? It's very simple. You just know how to find the area of like a square or rectangle. It's very easy. This is a little bit harder. Probably impossible actually, unless, yeah, impossible without like a calculator knowing the specific formula. So you wouldn't be asked to do something like this, but they might give you something like this isobaric, right? But just know that the work done is the area under the curve. And if you look here, isometric right here, you can't, how would you find the area under this curve, right? Well, you can't, right? And the area under this curve is nothing. It's like this. So it's actually like the area under this curve is 0. And that's because isometric processes, which are at constant volume, have a work of 0. And unless you change the volume, you're not actually doing work on a system of gases, right? Like the actual changing of volume is what determines whether or not you are or aren't doing work on the system. Okay. Next, let's talk about some important laws. Firstly is Boyle's law. It states that pressure and volume of a gas is inversely proportional under constant temperature. I'm going to explain what the law says, and then I'll show you what equation is derived from that law. Mainly what you really have to know is the equation, but it does help to know what the law states itself. So it states that the pressure and volume of a gas is inversely proportional under constant temperature. So P1 V1 equals P2 V2, right? I'm sure many of you knew that. Next up is Charles' law, which states that, and actually if you want to see this, you can see here that constant temperature, which is isothermal, this one, as the volume goes up, which is to this side, the pressure goes down, right? As the pressure goes up right here, the volume goes down, inversely proportional. So that is like a physical way to see Boyle's law. Next up is Charles' law, and which states that in an isobaric, which is a constant pressure process, volume and temperature will be proportional to each other. And the equation that we can derive from that is V1 over T1 equals V2 over T2. All right, very simple. And T, important to note, T is in Kelvin, not in Celsius. This needs to be in Kelvin, otherwise you might get a wrong answer. Okay? Because when you do things like if you are like kind of like doing ratios of like temperature to temperature, it doesn't matter. Like for example, if you did a change in temperature, sorry, not ratios in temperature, that matters. If you do like a delta T where it's a change in temperature, it doesn't matter because it's addition, subtraction. So it doesn't matter if you use Celsius or Kelvin. For multiplication and division, it does matter if you use Celsius or Kelvin because the numbers will be off. Next up is Avogadro's law, which states that in an isothermal and isobaric constant temperature and pressure process, volume and moles of a gas are proportional, right? So V1 over N1 equals V2 over N2, right? Really, mostly you just have to remember the equations, but it does help to remember the laws as well. Next up is Boltzmann's constant. The Boltzmann constant relates the kinetic energy of gas particles with the temperature of the gas. So, for example, the formula of Boltzmann constant equals PV over Tn, where N is the number of molecules of gas, not moles. Remember, molecules is moles with also taking into account Avogadro's number, multiplying by that. So the formula for Boltzmann constant is with molecules of gas, not moles of gas. And we know that the value of the constant is this, 1.38 times 10 to the negative 23. You don't have to memorize that, nor do you have to memorize the units. They will give you Boltzmann's, they should. I think I've always seen, if they ask for constant, I've always seen that they do give the value and the units of the constant, right? And they may ask you to find like P or find T or find V or something like that, right? And you just have to plug in the rest. Okay. So it would help mostly just to know this formula, right? Rather than the value of the constant. Okay, last thing for thermodynamics, I think, is coefficient of thermal expansion. This is a coefficient that is unique to each substance, and it is a measure of how much that substance expands per unit of temperature. The units of this coefficient are per degree Celsius, right? So this Celsius to the -1 is actually just 1 over Celsius, okay? And as you can see here, there's 2 alpha and beta. Don't worry about the difference between them. It's not too important. Just whatever one they give you, that's the one you use. Appropriate coefficients of thermal expansion for aluminum, concrete, diamond, glass, steel, and water. Obviously, if you have something like water, for each degree of heat or each degree of temperature that it changes by, it's going to get a lot bigger, a lot smaller compared to something like diamonds or like concrete, which doesn't get bigger or smaller really with temperature, right? Which, I mean, should make sense to you. Why something like a liquid does, and whereas a solid doesn't.